Hello, Kokones! It's me, Chase Yukone! And today, we're gonna talk about discrete mathematics. Hey, if I have to study, you guys are gonna study too. I have, the reason for this stream, actually, is because I have a little exam coming up for this class. And I thought this subject was pretty cool. So I was like, you know, the best way to study for something is to explain it to other people. So we're gonna do that. And also, I think it's really cool, discrete mathematics. And it's a little underrated, I think, out of all the other maths, you know? People are always talking about the 1 plus 1. Well, what about if I have a group of 10 people, how many ways can I rearrange those 10 people? What if one of those 10 people hates these 5 people? Then how many different ways can we arrange those people? Yeah. I thought it was pretty cool. Oh yeah, I'm currently setting up a whiteboard right now, so let me do that. Because I realized, yeah, I need to do that. I was originally gonna make this a ASMR stream. But my voice is kind of too dead for that right now. Contrary to popular belief, but whispering is actually very harmful for your voice. Well, I mean, like, it's not gonna kill it immediately, but it is gonna strain your voice a little more than if you just talked really quietly in your bass voice, you know what I'm saying? You know, so yeah, that's the thing. I talk like this for about 2 hours, I think my voice will actually die. You wanna know why my voice is all messed up? Little story. It's because my sibling and I were playing games yesterday. You know how siblings are. We were playing teamwork biblio games. So, yeah. Okay, but I am good to talk in my regular bass voice for 2 hours or so. So yeah. You're gonna learn what I took, like, what, 3 months to learn in 2 hours. So we gotta get started. Okay. Alright. What is... I have my notebook right here. I'm just gonna read off of here. So, and I would like to give a little disclaimer. I'm not a professional. I'm not even the top student in this class. I'm just a little guy trying to study. So, take everything with a grain of salt. If you're interested in something, feel free to research it. There's probably a Wikipedia page somewhere. But yeah, okay. Let's get started. Yeah. Okay. So, discrete mathematics. First of all, what is discrete mathematics? Well, discrete mathematics deals with discrete variables. I know, very, very surprising. What is a discrete variable? Well, first, there are continuous variables. These are variables that can be any number. Think your x's and your y's and all that good stuff. Yeah, it can be anything. Like, money, that's a continuous variable. Well, there's some things like... Yeah, it's basically a continuous... A discrete variable has limitations. And, yeah... Like a discrete variable will be like, it can't be less than 10, or it has to be a whole number, or stuff like that. They have some limitations. So we're gonna work with a bunch of numbers, or placeholders for numbers. We're gonna work with defined things. It's like, instead of saying, we have X amount of things, and X could be 0.3457891, we're gonna be like, we're gonna work with 10 things and only 10 things. Okay. Axioms are statements that are assumed without proof. We use axioms to kind of set the world or the situation of every problem. So in the scenario, Billy has 10 friends, and Billy wants to feed cake to each of his 10 friends. Those things are axioms. We don't need to prove that Billy has 10 friends. Honestly, I'm surprised that Billy has 10 friends. But anyway, we don't need to prove that Billy wants to feed people cake. He just does, and we know it. Okay, so yeah, we use these to set the world. Now, discrete mathematics deals with a lot of proofs and proof writings. You gotta prove things mathematically, which is kind of fun in a way, writing proofs, but also really it's hard. Okay, so yeah, we need to set the axioms to set the world in which we are using proofs to write in the world. Yeah, okay. Deductive versus inductive. Deductive means you take a general statement and you use it to get a particular solution to a particular thing. You go from the general to the particular. So it's like, if the general statement is all cats are dogs, and then the particular statement is therefore all ginger cats are dogs. My bad, that wasn't a part of the notes. Next is inductive reasoning, which is the particular to the general. So in that case, it would take all ginger cats are dogs, therefore all cats are dogs. Yeah, you go from... So deductive, you go from the big to the small. Inductive, you go from the small to the big. Okay, next let's go over some basic counting rules. Basic counting rules. How do you count stuff? 1, 2, 4? I don't know. I don't know anymore. Basic counting rules. Okay, number 1, the addition principle. The addition principle says if you have a set of some things and you have a set of other things, the total amount of things you have can be found by adding the number of things in set 1 and you add it together with the number of things in set 2. I know, that's so revolutionary. Yeah. I realize now that a lot of the stuff is stuff you've already been doing, but we put names to it and now it's fancy. Okay. Alright. So, yeah. Set A plus set B equals the total of set A and B. So if I have 10 rubber balls inside of a box, and we got hello Flopper, hello. Yo, what's up? The sky. That's funny. That's funny. I think what's up is discrete mathematics. We're so discreet about it. We gotta not tell anyone that we're doing discrete math. I'm just reading my notes here. I thought it'd be kind of interesting. I was like, I have to stream today, but I also have to study. Let's just do both at the same time. Yeah. Okay. Anyway, my example. If you have 10 rubber band balls in one box, and then in another box you have 5 cookies, how many rubber band balls and cookies do you have? You add 10 plus 5. This is the addition principle. Okay, yippee. Okay. Next principle, the multiplication principle. Okay, so you take your 10 rubber band balls and you take your 5 cookies in the other box. How many different ways can you put those cookies and rubber band balls? How many ways can you arrange those things? How many ways can you pair up those things? Well, you take your 10 rubber band balls and you multiply it by your 5 cookies. And that's how many ways you can pair up those cookies and rubber band balls. This is the multiplication principle. Yay! If you ever want to find out how many combinations of stuff, you just take it and you multiply it. And this is useful because let's say you have a combination code that's like 3 buttons, how many possible combinations are there where you can press like 2 buttons at the same time or whatever. You take 3 and you multiply it by 3. And now there should be 9 combinations. That means if I want to break into your home and you have a number pad, I know how many different codes I need to try out before before I can get inside. Hello, bunny! Oh no, math. Math isn't scary, guys. It's not scary. It's beautiful. And I want to show you guys that it's beautiful. Talking about it because it's beautiful. Yeah, I think so. Yeah, configurations of stuff. Okay, that's it. Okay. Number 3! Top 3 mathematical principles. The pigeonhole principle. Okay, if you have a bunch of stuff, and you have... Okay, actually no, not stuff. Pigeons. It's called the pigeonhole principle for a reason. You have a bunch of pigeons, and you have a bunch of holes. If there are more pigeons than holes, then there has to be a hole with more than one pigeon. Yes. So, yeah. Yeah. If you have twice as many pigeons as you have holes, actually more than twice as many pigeons as you have holes, then you have to have a hole that has 3 pigeons instead of 2. That's a lot of pigeons. That's a lot of holes. Okay, cool. Okay, how do you... So this is where we're trying to... Hello! Hello, Hazel the tree! Hope you're doing well. Discrete mathematics. This is like an audio-only stream, kind of. I do have a whiteboard in case I need to draw stuff, which I think we might need to draw stuff in like a second here. It's not too much. It's too much. Yeah. Learn about fun facts. Fun facts, guys. Oh shoot, I just dropped my pen. Okay, next up. Okay, more on the pigeonhole principle. There's a little formula you can use to guarantee that you have more than one pigeon inside the hole, which is you take the number of holes and you multiply it by the number of pigeons minus 1, and then you add 1 that. Wait, yeah. And that's how many... That's how you get how many pigeons you want in one hole. So if I want 3 pigeons in one hole, then I'm gonna need to take the number of slots. So let's say my number of slots is like 4. I have 4 holes for... Have I been saying slots or holes? Holes. I have 4 holes for the pigeons to go into. So I take 4, and then I want... Wait. 3 minus 1, which is 2. 4, wait, that's 8 plus 1. That's 9. Wait. I gotta write this out. Why does it... You ever like write notes and then read them back and be like, what are you writing about? Yeah. Yeah, so many pigeons in holes. You want pigeons in holes? Yeah. Yeah, it says guaranteed M pigeons in one hole. So it says take the number of holes and multiply it the number of pigeons minus 1, and then add 1 to that. So I have 4 holes times... I want 5 pigeons in one hole. So 4 times 12 plus 1. So that's how many pigeons I should have? Wait, 4 times 3 plus 15. And then I have 4 holes. Oh yeah! Yeah, I should have I should have that many pigeons. Okay, we're good, guys. That's how many pigeons. Yeah, okay. Anyway, let's write a proof, guys. You guys want to write proof? Yeah. I'm gonna show you how to write a proof. Let me show you. One button is this. Hey, I have a whiteboard. Okay, check this out. Okay. So, what do we use the proofs for? We use it to prove things in math. Like, we don't know 1 plus 1 equals 2 until we prove that 1 plus 1 equals 2. It's like you're in an argument with someone and you're like, how do you know that? Well, I'm gonna show you how I know that, okay? First, we're gonna write on the top of our formal proof. I just dropped my notebook. That doesn't matter. We're gonna write. Oh my god, why do I have a... Oh, wait. Hold on, I have to... My pen is not working. Okay. Do I have to restart? Right click. Okay. Whoa! We're gonna have to restart that. Give me a second. Give me a second. Yeah, in a formal... There's different kinds of proofs, so we'll just walk through them. So, the first kind of proof is a... There's a proof called a constructive proof that says there exists... You use that to prove that something exists. For example, if you want to prove that there is an odd prime number, then you would be like, there exists a prime number with the property of being odd, and then you would go on and prove. And then there's another proof where there's a... Come back. What other proofs are there? There's proof by exhaustion, which oh, thank you for the follow! Thank you. I gotta go on to... Wait, I can't read. Wait. Thank you for the follow, Arietta. Ooh, woo. Thank you, welcome. Okay. Okay. The next one is proof by exhaustion, which isn't as hard as it sounds, okay? It's not like we're gonna prove a bunch of things and go, I'm dying here! So, it's, So if you have a finite set, which means it's not infinite, like if you have a bunch of cases, you would go by and prove that all of those cases are that thing. So for example, if you want to prove that there is only one end, okay, like you say you have a list of choices, okay, right? And you want to prove that all of those choices eventually leads to you. How about all choices lead to spaghetti, okay? Then you would go through every single choice you have and show how that eventually means you'll end up eating spaghetti. So like the first choice, the first choice is I either wake up or I don't. And then you gotta prove, okay, if I wake up, then I'm gonna go downstairs, I'm gonna eat spaghetti. That's what you gotta prove. And then for the second case, I don't wake up. Well, if I don't wake up, I gotta prove that I will end up eating spaghetti. And then once you prove that, and then you go through that for every single possible case, until you prove everything leads to this one thing, and therefore that thing must be true. That's a proof by exhaustion. It is quite exhausting. The next kind of proof is proof by counterexample. So, if you have a statement that's like, all bees are stupid. But, if you say all bees are stupid, then I would say, counterexample, this is Lemmy the bee. And Lemmy the bee can write words. And Lemmy the bee is smart. Therefore, not all... There exists a bee that is smart. Therefore, not all bees are not smart. That's counterexample. Okay, I have the thing set up. You guys want to write a formal... Where is it? Okay, there we go. I had to select my color, but this is how we write a formal proof. So, I want you guys to use this in the most petty way possible. Okay, if you have next time you have an argument with one of your pals or one of your friends, I want you to pull something like this up. Alright, first, we're gonna write our theorem. A theorem is basically what we're trying to prove, alright? Let's say in this scenario, you're trying to prove that your friend is let's be nice today. Your friend is cool. Theorem, you are cool. Okay, so you're gonna write your theorem at the top, all fancy like. Then you're gonna go right. You have to write the word proof. And people usually write this in italics or like I'm not really the best at that. So yeah, you write theorem at the top, you write proof. Okay, and then you write your definitions. The definition of cool is you. No. You write your definitions. Alright. You could get your definitions from like anywhere. You probably have to cite your source. But you get your definitions, your widely used definitions. You can come up with your own definitions and stuff. Okay, so the definition of cool is you. That's your definitions. After that, you gotta write your actual proof. Okay, so actually I'm gonna say the definition of cool is awesome. So first thing, you are awesome. Yeah. And so this is where you like prove that you are awesome. And then after you prove that you're awesome, you would end this by going, by definition of cool, thus, you must be cool. And then you would end the proof with a little... Oh. It's usually just a square, but I usually add like a there. But yeah, this is our proof. Oh. This is our proof, guys. Stop it. Stop. Yeah. I'm trying to make it so my face like doesn't. I can't do it. I have to be angry while presenting. Okay, this is our proof. This is how basically all formal proofs go. My proof? I don't know. It's just how it is. Yeah. Yep. There's a lot of different words that you could put into proofs. You know, a lot of common words that you'll be seeing inside of formal proof are, your, proof. Sometimes in proofs, you gotta assume things in order to prove them. For example, if you're proving an if-then statement, you just assume that if is true. You don't need to, like, prove that if is true. Because then, an if-then statement is only true when the then is true when the if is true. If I say, if I was as tall as a tree, then I would be a vegetarian. You only have to assume that I am as tall as a tree, because we're only trying to prove the relation between me being a vegetarian and me being as tall as a tree. If I am a vegetarian but I'm not as tall as a tree, that doesn't necessarily mean that the if-then statement isn't true. Like... yeah. It just means I'm a vegetarian. But if I turned out to be as tall as a tree and I wasn't a vegetarian, then that means the if-then statement, the if-then relation, is not true. Because I'm not a vegetarian even though I am as tall as a tree. Right, that's... What other kind of proofs? Oh, a direct proof. So, a direct proof does this. It's a if-then statement kind of proof. It's like, you assume... So, if you have two statements, A and B, and you're trying to prove if A then B, you would first assume A is true, and then show that because A is true, B must also be true. Yeah. Yeah, those are some proofs. Do I have more proofs in here? There's another one later on. That's like a combinatorial proof? Combination proof? Proof by combination? Combinatorial? I don't know. Combination. Competent. I'm competent. But basically, in that proof, you would take two things and then you would prove that they're the same thing, just in different orders. Or different... Like, hold on. Let's go back to the whiteboard. Let's go back to the whiteboard. I'm trying to prove that this is the same as this. Therefore, I would use a combinatorial proof to show that these two things are the same thing, just in different orders. And a lot of these combinatorial proofs utilize real-world examples. So sometimes some of them would be like, suppose you have 3 blocks. On each of the blocks is labeled 1, 2, and 3. And you have other blocks that say 3, 2, 1. Well, if you look at the left-hand side, yeah, that's you could rearrange that. You could move the blocks around to get 3, 2, 1. And on the right side, you could rearrange the blocks to get 1, 2, 3. Therefore, 1, 2, 3 must be equal to 3, 2, 1. I'm coming up with these examples on the spot, so you know there might not be the best examples, but I think they work. They get the point across. Okay. Set notation. Let's talk about a bit of fancy math notations. Math people save a lot of time with a lot of things. Math people with all the time they save when they turn with respect to into wort. WRT. Oh, we save so much time. Whoa, guys, look! There's flying birds and no, flying planes. Yeah, I don't know how to draw a plane, but this is a plane. Yeah, they're flying planes now with all the time we spent. Oh, we have hover car thing, that like hover pods. Oh my gosh, and we have like, God, guys, got little circular cars, and we have giant computer hologram with all the time that we save. Look at all the stuff we've been able to create because we turned one word into an acronym and we saved so much time instead of writing the whole word out, guys. Wow, this is so cool. Okay. That. Set notation. Set notation. Wait, I'm on the other side. Okay. So, or just notation in general. Okay, so a set is a collection of a bunch of things. So like the alphabet is a collection of letters, and each letter is an element of the alphabet, right? Just like my set of friends, and all my friends are an element of the set. So how do we say is an element of? We use this guy. We use this guy right here. Yeah, this little guy right here. Okay, I'll write it out for you guys. This means is element of It also can stand for is in if you're more simple like that. Like, I am in the set of cool peoples. I am in the set of the awesome. Therefore, I would use me awesome. Yeah, so that's how you would use that notation. We save so much time instead of writing that. It's great. Next up, on the contrary, we have cross a line through it. It's is not in or is not an element of. So this letter, do we know what this letter is called? I don't know what this letter. It's some Greek letter. But anyway, yeah, this one, if you cross a line through anything, it just turns that thing into not. And I mean anything. Anything. This little symbol right here is empty set, which means it's a set that contains literally nothing. So let me show you what a set normally looks like. So if we have a set A of awesome, and that, so we have brackets to represent like, and we use commas to separate the elements. So in the set of awesome, we have you, we have Billy. Remember Billy from earlier? Yeah, he's also in the set of awesome. Okay, so this is what a normal set looks like. This set has 3 elements. This is the set, like, A's set A for set awesome. So yeah, this is our set. Cool. An empty set, which we're gonna call set E, looks like this. There is nothing in there. This is not to be confused with a set that has 0 in it and nothing else. This is still a set. This is not an empty set because there is 1 element in here, and that's 0. But an empty set just straight up has nothing in it. It's like you have a box that's empty. Meanwhile, this 0 set has a box with just a 0 in it. There's a couple more we have to get through. This one's for subset. So if I have, in the set of awesome, and the set of me and you would be a subset of the set of awesome. So if the set of cool contains me and you, and the set of awesome contains you and Billy, then the set of cool is a subset of the set of awesome, because everything in the set of cool is contained within the set of awesome. Isn't that awesome? And then we have this other notation, which is a subset of or is equal to. So for the regular subset notation, it's just like subset with a line underneath it. Anyway, this means that set of cool could contain Billy, so the set of cool now contains Billy. It contains every element of set awesome. Therefore, C, or set cool, is a subset of or is equal to set A. So if 2 sets have the same elements and they contain every element of each other, they are equal to each other. Those subsets equal to each other. They're equal. They're the same. Also, when you write stuff in set order, it doesn't, or set, when you write things are an element of set and you're listing out the elements, there's no order that you have to put them in. So yeah, I could put me, you, Billy. I could put Billy, you, me. It's still the same set. Who is Billy? Here's some other ones that save a lot of time. You're gonna love these. I think all your friends are gonna love these when you use them against them. But such as, that's right, such as is just a line. So it's like the set elements of set A. So I guess we could say X, which is used to represent elements. Elements of set A. Wait, no, this isn't such as. This is such that. Such that. My bad. My bad, guys. My bad. So, such that, not such as. I don't know why I wrote that in my notes. But anyway, okay. Such that. This straight line right here, this is such that. Such that. I'm repeating it a lot of times so that it gets into your brain what it is. Yeah, such that. Such that. Okay, anyway. Elements of set awesome such that the elements are in set cool. So if we say set cool is me and you, and then we say elements of set A that are such that are also elements in set cool, then we're really just talking about me and you, because me and you are the only elements in both set awesome and set cool. If that makes sense. So yeah. Such that is basically just like how you added a little modifier to your stuff. It's also like saying, blah blah blah, where this property, blah blah blah. So like, if I pick 2 red coins inside of my coin hat, such that the coins have a price worth of 5 nickels, then yeah, that's like a add-on there. You're not just picking red coins, you're picking red coins that have a price of 5 nickels. Can you tell I'm making these on the spot? Okay, so another set that we should pay is the universal set that is determined by this lovely U. So a universal set is a set that is, well, universal. It's like it contains every element ever. Okay, so if set U is everyone, I'm not gonna write out all the elements of set U, but if we say set U is everyone, well then we have set C, which is set cool, which is me and you, and then we have set A, which is, I forgot to write out the notation. Ugh. Me, you, and Billy. Then the universal set would contain me, you, Billy, and maybe more stuff. You know, me, you, Billy, Bobby. Me, you, Billy, Bobby, Boingy. The set you would contain everyone. It would contain everything and everyone. It's the big set. It's like everything. Yeah. Everything is a subset of the universal set. Don't you forget that. Don't forget that. Okay, next up. We are done with. Here's some more fancy symbols, guys. I'm gonna write them. I'm gonna show you what each of them mean, okay? Oh, I messed it up. That looks really bad. Oh, I'm not doing a good job at drawing these guys. Great, here's a bunch of cool looking letters. You might think this is just a regular cool font, but it's not. It's math, guys. Everything's math. Okay, let's look at this fancy N here with 2 lines on it. This fancy N is the set of natural numbers, which is it's do a different one first. Okay. I think we should start with this one actually. Okay, let's start with this fancy Z here. This fancy Z with 2 lines is the set of all integers And integers are basically your -0, your 1, your wait, what? No, -1, 0, 1, 2, 3, and then it's the numbers that don't have decimals. It's those numbers that aren't fractions. Those numbers that aren't weak. It's the ones you use to count all the time, but they can also be negative. The set of all integers includes all the non-decimal, all the non-irrational boys, all the rational guys, and they can be negative or positive. So yeah. Now let's go to the W. The W is whole numbers. The whole numbers includes all integers that are equal to or greater than 0. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 7. I'm sorry, guys. Anyway. That was actually pure instinct. What is wrong with me? I tried to stop myself, but the pull is too strong. Oh my gosh. Oh, congratulations on your 5-stream watch streak, buddy! Yippee! I think I need to put myself in the timeout corner, honestly. I think so. I'm gonna need to take a breather. Six, 7, Rokunana, 6, 7. Okay, anyway. The set of whole numbers is all the integers that are greater than or equal to 0. Yippee. Now let's move on to the natural numbers, which is this weird looking N here. So this weird looking N is the set of natural numbers, which is anything greater than all integers, by the way. So no decimals, no nothing. None of that weird stuff. It's everything greater than 0. So it's just 1, 2, 3. It's the stuff you use to count things. 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, 14, 15. All that stuff. Next up is the Q. Over here, this fancy Q is a set of rational numbers. Which rational numbers are all numbers that... These are, this includes integers, but it includes anything that can be written as a fraction using integers as the numbers. Okay, so rational numbers is like, it can be written as a ratio. For example, if you ever heard of 0.5, that can be written as 1/2, which 1/2 are both integers. And you also have something that's like 0.66666666 repeating. I'm sorry if I just cursed you, by the way. Numbers aren't cursed. Numbers are numbers. But yeah, that's can be written as, if you don't like that notation, well, good news. You can write that as 2/3, and 2/3 are both integers. Yay! We got a couple other ones, like, what is another one I can name? 0.20 can be written as 1/5. I think 3/8 can be written as 0.375, if I'm not mistaken. So yeah. And you know that 3 and 8 are integers, so therefore all of these little fractions, these are all rational numbers. And rational numbers also includes the integers too. Yeah, and it also doesn't include anything where the denominator is 0, so like 4 divided by 0 is not a rational number. It doesn't even... anything divided by 0 is weird. Okay. Next up is irrational numbers. So let's go over to this. I think this one is irrational numbers. Irrational numbers are numbers that are not rational. Okay, moving on. I wish I could give you a better explanation, but that's really all I can muster up. You see, when I talk to people and they ask me about something and I say it's too complicated, it doesn't mean I think it's too complicated for them to learn. It means it's too complicated for me to explain. And I'm telling you, all I know about irrational numbers is that they're not rational. Maybe that's the actual definition, but I have no idea. I have no idea what irrational numbers actually are. So they're just they can't be written as a ratio. Maybe that's their whole shtick. I don't know. Okay, real numbers is the entire. This is the R thing right here. This one. So Q is for rational numbers and R is for real numbers. Real numbers include the entire number line. The entire thing. Yeah. All the irrational numbers, all the rational numbers, all the natural numbers, everything in here is in the number line. It's in real numbers. I think that's correct. Yeah. Complex numbers. If you ever heard of I, which equals the square root of -1, those are under complex numbers. They're weird. So these are the weirdos. Yeah, so yeah, these are all numbers that involve I in some way. They're complex. Those little C with 2 lines. They're weird. They're complex. They're not like everyone else. Their mothers don't understand them. It's not a phase. Yeah, so what if I'm different? So what if I'm complex? I have a negative square root of I or 1 Okay. There's a lot of notation. I was hoping to just kind of read these, but there's a lot of notation. Of course we know our set notation and our subset stuff, so we're not gonna go over that again. Let's go with... I'm gonna use B. We're gonna make a new set, guys. The set of Blaze. The set of Blaze. And we're gonna do the set of Awesome and the set of Blaze and the set Awesome with this other one. So this right here is union. And this one over here, this N looking thing, is intersection. I can't fit that, but that says intersection. So this means the union of two sets is everything in both sets without any duplicates. So for example, we said in set Awesome it's me, you, and Bele. Let's say in set Bele it's Bele, Babe, and Boingy. Bele, Babe, Boingy. Okay, so the union of set Bele and set Awesome would be me, you, Billy, Buggy, Boingy. Yeah, it just like adds everything together and it removes any duplicates so that the duplicates only appear once. That's what a union of two sets is. Yeah. And then an intersection of two sets is the collection of the duplicates. It's everything that is in both set Awesome and set Billy. So if we take a look at set Awesome, which is me, you, Billy, and the set Billy, which is Billy, Bobby, Boingy, the intersection of sets A and B, set Awesome and set Billy, is just Billy, because Billy is in both set Awesome and set Billy, and it is the only element that is in both of them. So yeah, it only includes Billy. There's some... So here's another notation thing. Usually in other areas of math, these two straight lines would say absolute value. In discrete mathematics, or set notation and stuff like that, these two lines represent the cardinality of a thing, which basically says, how many things are in this thing? So in set Awesome, we have 3 things. Therefore, the cardinality of set A is 3. Me, you, and Bele. That's 3 things. We can count. Remember those counting principles, guys? Yeah. Another little vocabulary thing is disjoint. To be disjoint means the intersection between two sets is an empty set, which means that there are no elements shared between the two sets. So let's say Billy didn't exist, so set awesome was just me and you, and set... Or actually no, let's just use set cool. You remember set cool from earlier. Set cool is just me and you. The intersection of set cool and set Billy, which contains Billy, Boingy, and Bobby, is empty because they share no one in common. Therefore, set cool and set Billy are disjoint. Yeah. That's a fun fact for you to never use. I want to skip past some. Let's move forward with this. I don't care about this. There's a notation that it can look like this, or it can look like this. It doesn't really matter. This just means all the elements of set... Wait. Okay, so it just says... This just excludes all the elements they share. So this is set difference. So the set difference of set awesome and set Bele is just me, you, Boingy, and Bobby. Because we don't want Billy anymore. Yeah, it just crosses out stuff they have in common. Or it basically says anything in set A minus anything in set B. So like any elements that are in set B that are in set A, we don't want set B. Anything in set B, we've got to get out of here. We have A cross B, which basically says we just pair up all the things. So for example, an element of, let's say A cross B is equal to element doi or set doi. One of the elements in set doi would probably look something like this. Me and Bobby. And then another element would look like this. You and Boingy. So yeah, it basically pairs up all of the different elements of the set to get these ordered pair looking things. And those are the elements of set doi. This is called a Cartesian product. I'm tired of sets. I don't want to talk about sets anymore. What can we talk about? I want to talk about something that doesn't require a whiteboard. I'm sick of drawing. I'm sick of drawing here. Okay. I hate drawing. No, I love drawing. Let's move forward to something more. I want to talk about graphs. Okay, so another thing. Proof by contradiction. It basically says assume if you have a statement that's like all cats or dogs, you assume the opposite of the statement, which is all cats are not dogs, and you show how having not all okay, I need to use stuff. I keep using examples that are just not true for proofs when we're trying to prove that things are true. Hold on. Okay, all black cats are cats. There we go. That's our statement. So we therefore assume that all black cats are not cats, and then we show that all black cats not being cats leads to some kind of contradiction with something. So like, if we assume all black cats are not cats, and then we're like, but the definition of cats says that cats are cats, that's a contradiction. Therefore, because all black cats are not black cats, that's false. All black cats must be cats. Yeah! Okay, I'm gonna skip ahead. I want to talk about Yeah, let's talk about fun stuff. Like graphs. You guys like graphs? I like graphs. Okay. So, a graph is... A graph is a collection of vertices and edges. You guys know those? Vertices and edges? Edges. So yeah, vertices are the little guys, and then edges are lines between the little guys. They're connections between the little guys. And while most graphs tend to look like, you know how they, dang it, I have to draw it. Okay, I guess we're drawing again. Okay. Okay, so a vertex looks like this. Mostly. In most notations, they look like this. This vertex and a little guy. Hello, vertex. Vertex. I spelled that wrong. That. Vertex. The little guy. And then you have another little guy. You connect those little guys. What do you have here? This is an edge. So an edge connects two little guys, or two vertices, right? And the whole thing here is a graph. Yeah. That's a graph. You like graphs? I could add another little guy. I could connect these two little guys together. My really bad lines. And this is another edge. It's still a graph. These guys don't have to be connected over here for it to be a graph. It's just, yeah. It doesn't even have to look like this. This is just a common way of doing it. It can look like this. Kind of weird, right? It can literally just be... It can be something like this over here. That it doesn't have to look like that. So yeah, these are like what kind of... There's a lot of different ways you can write how a graph looks like. So yeah, have fun with that, I guess. How do we write a graph? I don't know. Do some math. So yeah. We're gonna be talking about simple graphs and stuff where we don't want to do any loops, which means like something is connected to itself, something has an edge with itself. So it's like if this guy over here had a little loop like that. We're not gonna talk about that for today. And we're also not gonna talk about some like weird ones where like this guy has two edges with this guy. What? No, we're not gonna talk about that. I don't understand that. Okay. Two graphs are the same if they all share, number one, they all share the same vertices, and then they also share the same edges. And yeah. And that's called being isomorphic. Isomorphic. Iso awesome, isomorphic. Two graphs are the same if you could prove that they have the same edges and the same vertices. And they could be rotated, they could have like the vertices in different places, but if you can prove that they have like the same thing, just different ways, yeah, then they're the same. Okay. A cycle is basically a cycle. Cycle. It's something like this. Or it can look like this too. It basically, yeah. It can also be a square. Yeah. That's all I have to say about cycles. So yeah, a cycle has a path from a vertex back to itself. Yeah. Oh yeah, by the way, a path is a sequence of vertices. Yeah. It's just like the different orders of them. They're usually connected by edges. So like if I go from like here to here to... That's a path. Actually, there's no edge there, we can't go there. But yeah, if we just like travel along this thing, reverse the path. Oh yeah, how awesome, guys. Yeah. Connectedness means a graph is connected if you can get to any vertex from any vertex. Vertex. So yeah. An example in this pentagon here. If I want to go from, let's say, A to E, I have a path to get there. If I want to go from A to D, then I have a path to get there. I also have a path to get from A to B, and I have a path to get from A to B, and yeah. And the same thing with every other thing. We have paths to get to anywhere here. Like, therefore this graph is connected. Another connected graph, I think this. Something like this. You could go from D to A, D to... From A, you could get to A and... A is there, and then A, B. There's a path to go everywhere. Therefore, that graph is connected. Redundancy means that there are multiple ways to get to one thing. Like, there are multiple paths you could take to get to any vertex. So, for example, if I added like a path of... I'm gonna write this in a different way. So if we have something that looks like... Then there's multiple ways to get to anything. So, like, you could go from... Let's say to get from... Let's talk about A and B here. So to get from here to here, you have this path. Also take... You can also take this one here. You can also take this one here. And there's like multiple different ways you can get there. So that's awesome. That's great. Sometimes we want to have redundancies. Especially if you're like actually using stuff. Like if you're using a graph to represent how to get to places or places to go, having different paths to get to places would be pretty awesome. There are a couple different types of graphs. One of those graphs I like is called a complete graph, where every single vertex is... You have a direct path to every single other guy. So let me show you a complete graph. And we would label this KN. So in this case, I'm going to show you K5. So as you can see, this is also did I make it look weird? Okay, no, it's fine. As you can see, there are okay, don't mind that area. That so like if I want to go to everyone's houses, I have a direct path to everyone's houses. We could go from here and here, and it's like here, and it's like yeah. I should use a different color to show you guys. I am gonna use a different... Here, have this nice, weird-looking red. Like, I could go here, I could go here, I can go here, I have over here. So yeah. We could go anywhere. And that's a complete graph. Isn't that cool? Isn't that real cool? That's real. That's so cool, guys. Moving on to graph colorability. So, you can color graphs. That's awesome, right? So... here we have a graph. Actually, I'll make it 4. So I can make this one red. I can make this one yellow. That one doesn't really show up, but you know. I can make this one blue. We could keep that one as black. So this is us coloring the edges. We're gonna use... actually, no, we're gonna make you green. I like green. You guys like green? I like green. So this is a graph. Yeah, lovely, lovely graph. I'm gonna say the word graph a lot. Yeah, we can make connect. Color the verse. Very cool. Very awesome. Very cool. We can also color the edges of the graph. On a red edge. That's black. That's not red. That's dead. This is red. Orangey. Could be blue. This one's kind of uglier than this one, but you can kind of see it, right? You can color the different edges, different colors, and you can use this to cool. You can use this to do a couple of cool. What the heck? You could do a couple cool things, which is you can make a bipartite graph, which basically means you color... yeah, I don't like that color. You color every vertex into 2 colors. So let's do pink and blue. I like pink. This is an ugly blue. Why do I keep choosing such ugly colors? Alright, look at that. Look at that. We got, yeah. And a bipartite, means that we gotta have different colors of vertices when we make an edge. So we can't have an edge between 2 blues, and we can't have an edge between 2. So we can only have edges like this. This is our... this is our complete bipartite graph. And we would write this as 2, 3. Which basically, how many vertices is in one color and how many is in the next. Here's the fun thing, guys. I'm gonna show you a fun fact. It's still an ongoing thing to study. We don't know how many... how do I say this? So these bipartite graph problems are still unsolved. Or at least a lot of them are. We're trying to find the... give me a second. Ah, okay. Ramsey numbers. That's what I was trying to say. Okay, so a Ramsey number is the smallest number where a... Okay. Let me show you. Let me show you these Ramsey numbers. Let me show you. This is cool. This is actually cool, guys. All right. Okay. So we can color edges, right? We talked about that. We talked about how we can color edges. Let's do red. I think. So we got a bunch of red edges and we got a bunch of green. My bad. Okay, so finish me. So the Ramsey number is basically a number or a graph that... Hold on. It's basically a graph where we try not to make two edges of the same... a cycle of edges of the same color inside the thing. So... what the heck? Give me a second, guys. My brain... I haven't looked at Ramsey numbers in a while, but this is cool. I swear this is cool. Okay, so in a graph 3-3. Okay, let's keep it simple for my sake, by only talking about numbers. Okay, and we're gonna make... So, what we're trying to do is we're not gonna try to make any cycles of using one color or the other color. We don't want cycle. Why are you so ugly? Oh my god! Get out of here! Get out of here! So the Ramsey number for this. Let's see. Is it 4? 4 vertices. And so these things have to be a complete graph, by the way. So we need to connect every vertex to every other vertex. We need to make sure that this... So this is a complete graph, where everything is connected to everything else. But we want to color the edges in a way that none of these edges form a 3. We don't want any triangles. So let's try this out. Let's try... So I'm gonna start by making this edge red. And so therefore, I can't make this edge. And I can make this edge red. I can make this edge red. Yeah, that's... and if I look at this, I can't make this edge right here red. If I made this one red right here, we would have a triangle. Let me look like. We would have a triangle here of red. We don't want triangles. We hate triangles. So yeah, we would have to color this one green. Okay. What else do we have to color? I don't have to color anything else now, so color this one green. Color this one red. So we have one more edge to color here. So as you can see, we have 2 reds here, therefore we must make this one. And then I'm going to color this last one. And as you can see here, in this coloring, we have no cycles of 3 edges. Now you might be like, wait, this is a red triangle. It's not, because there's no vertex here. These are just from connecting these, like these. And I need a different color. Let's do black. They just happen to be crossing because of how we drew the graph, but if we drew it in a different way, these would create a triangle. What we're actually looking for is triangles. That one, or triangles of this one. And as you can see, all these triangles have 2 different colors in them. Therefore, the Ramsey number must be greater than 4, because a graph of 4 vertices doesn't force us to have any triangles of, or any cycles. of the same color. And this is an unsolved kind of math problem because we're still looking for Ramsey numbers of graphs that have let me search it up right now. Actually, let me knock your socks off by some unknown math. Undiscovered C numbers. There's papers written about this stuff. That's kind of cool. That's cool, guys. That's so good. Yeah, so one of the numbers that hasn't been discovered yet is Ramsey number 66, which basically says how many vertices do we need to make sure that we don't get any hexagons of one color, hexagon edges of one color. And yeah, that hasn't been discovered yet. I don't think you could take a crack at it though. Some theorize that the heat death of the universe will arrive before you find it, but you never know. You never know. Let's go ahead and talk about over here. Let's talk about some more graph coloring stuff. Some other facts about graph coloring. Yeah, so graph coloring can also be used to determine scheduling. So you could draw a graph with a bunch of like friends, and then you make the edges like conflicts between those friends. And then you could color those edges and stuff. Or you can use those guys. You could make a graph, and then you can like use a graph to visualize a lot of things. So I think you guys should use graphs all the time, because I think graphs are really cool, and you can use your crayons to color the graphs a bunch of different colors. And I really think that's cool because like graphs are cool and I like coloring. Okay. So yeah. Some things about graph coloring. So adjacent vertices, which as we said are like directly connected to each other, they just have like that shared edge. They should have different colors. Edges that share a vertex have different colors. Yeah. And ooh, faces. Let's talk about faces real quick. So we have some special planar graphs, which you might have heard of them before. I'm not sure. I don't know. But these are graphs that yeah. Planar graphs are not plain, guys. Planar graphs are a definition. Okay. There is one way to draw the graph without crossing edges. Okay, cool. So this right here is a planar graph. You might be like, how is that a planar graph? Well, if you rewrite it in a different way, you could move the edges like this. And therefore, this is you could draw in a way where the edges don't cross. Or if you just simply rearrange the points, like you swap 2 points over here, you could draw it as a square. These are pretty cool. So these planar graphs that don't have edges crossing, they have faces to them, and a face is, well, this is a face. It's basically like a little thing, the thing inside of the edges. You have a bunch of edges. I'm gonna say edges a lot today. You have a bunch of edges, and you have these things. Yeah, I got a triangle here. You guys like triangles? I like triangles. You got a triangle here. The triangle's happy. Yeah, the triangle has a face. Not only does the triangle have a face, but everything outside of the triangle also is a face. Therefore, this graph right here has two faces. That's right. When we talk about planar graphs, when we count the number of faces, we count the outside as well. And we could also write down the number of vertices this has. This has 3 vertices, and this has 3 edges. What a happy triangle! I love a happy triangle. It's so cute triangle. A triangle. Oh, triangle! You might know about... So, this is a guy named Euler. He has a number named after him. His name's kind of spelled like this way. Euler was kind of a cool guy. He made a lot of math. He's got the little E. You guys know E. Yeah. Well, Euler had a little formula about these planar graphs, and he said the number of vertices minus the number of faces is equal to the number of edges plus 2. And this is for any planar graph. So if you want to find out how many edges something has, we got this little formula here. That's cool. That's cool. Now here's the thing. There are 2 subgraphs. If any graph has... Oh yeah, a subgraph is like a little graph inside of a graph. You know how like subsets? Yeah. So if you have like a little pentagon that has like a big like here. It's so sloppy. You got a little triangle in here inside this pentagon graph. A little triangle is a subgraph of it. So anyway, if any graph contains a subgraph of the following, it's not planar. Which means there's no way you could draw it without crossing. And this is cool. I think you guys are gonna recognize at least one of these. So, yeah. Oh, hello! 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 Hello, Nero Spam. Hello. Greetings. Hello. I'm gonna show you something cool, actually. So, if we recall, so these are 2 graphs that we cannot draw without any of the edges crossing. So the first one is this graph here, complete 5. We got 5 vertices, and we want to connect every vertex to each other with like one edge, you know, we want a direct path. So we could do that. We go from A to here, we go from here. Okay, those are connected. Go from here. Okay, all of those are connected. That's great. We could put these 2 guys together. Put these guys together. Okay, that's looking great. That's looking great. We got these 2 guys. Okay. Cool. So I'm gonna focus on this guy. So this guy's already connected to these 2 right here. But we want this guy to be connected to this guy. And also this guy. So I'm gonna draw a little loop around here. Cool. Now this guy's connected to everyone. What about this guy? This guy's connected to this guy. This guy's connected to that guy. And that guy. We need him to get to that guy. Oh, and we also... Wait, okay. I also want to connect... That guy's connected to that guy. That guy. That guy's connected to that guy. That guy. And that guy. Okay, so all we need, our last connection, is to connect these 2 guys together. But there's no way where we can draw this graph where this guy gets connected to this guy. It's impossible. We have to cross them. We have to cross them. I'm not crashing out. Anyway. Yeah, so yeah. That's, yeah. So, if you want to frustrate your friends, tell them to try and find a way to connect this graph without the edges crossing. That'll keep it busy for like 2 hours. Here's one that I think a lot of other people have attempted. Okay, so I'm gonna use 2 different colors. I'm gonna use purple. We haven't used purple. Okay, so you've heard this problem before. We got 3 houses. And we have, 2 green. I know we used green before, but I really like green. And we have 3 utilities. Water, electricity, and heat. Or water, electricity, what else do people use? Gas? Water, electricity, and gas. So let's try and connect these graphs in a way where every house gets all 3 utilities without any of the little supply lines crossing each other. You got me stumped in this field. I never studied discrete maths. And I think discrete maths is fun because there's a lot of puzzles that, you know, there's a lot of puzzles that people talk about and it's from discrete maths, but they never know. So I wanted to talk about these little puzzles. Okay, you've heard of this one. It's the 3 utilities problem. Okay, let's try and draw a way for these graphs for these guys to get all 3 utilities without crossing. Let's start with house 1. The house 1 we can go like this. And I'm gonna go around here actually. I'm gonna give a lot of space. Like a lot of space. Right? Okay, so this guy has all 3 utilities. What about this guy? Well, we can't cross through here. That's a no-no. We can go here. Go like, and then we could go here maybe? And then this guy could go through here. He could go through here. But there is no way for us to get, like, inside here. There's no way for us to get to that guy. Let's try a different way. I know, like, you might be like, what if you just did, like, this instead? Okay. So we do that. And then we do this. Like, that guy has 3. Go over here. And then we go through. There is no way for this guy to get over there, either way. And maybe you're like, I don't believe it. Okay, go this way. Okay, I do go that way. Oh. Okay, we could go there. See, now we can get to the first one. We can't get over here without crossing anything. So this little problem is completely impossible. And I remember trying this when I was in, like, school. Well, I'm still in school. But I mean, like, I remember trying this when I was a youngin'. And then all my friends tried it. And then we couldn't do it. Little did we know it was impossible. So yeah, if you want to keep someone busy for a while, just give them these. They're just gonna sit here and do them, and it's impossible. Yeah. This is why my house doesn't have water. Exactly! Exactly. Because they can't draw away. They can't draw this graph without anything crossing. So actually, your water is going to my house. And, I'm sorry, I need this water. You can have 2 droplets. I think maybe there is one way to do it, which is to bend the paper or cut a hole through the paper. Let me show you what I'm talking about. Okay. theoretically, if you were to cut a hole through the paper, which I can't do that because this is a virtual whiteboard, if you cut a hole through here, then you can make the hole come out, and then you could go through here. So if you want water, you gotta cut a hole through dimensional space and time. I think that's pretty simple though. Just ask your landlord to do that. He might charge you extra. Okay. What do we? So in a planar graph, there is wait. The reason why I talked about planar graphs in the first place, we were talking about colorability. Oh yeah, right. Okay, little note about that. So yeah, faces sharing a vertex have different. What? Yeah, I'm supposed to say edge. Yeah. So if two faces, what the heck? If two faces share an edge, we could color them different colors. That's pretty much it. And if two edges share a vertex, or two vertices share an edge, those are different colors. If two edges share a vertex, there are different colors. Yeah. There's different ways we could color a graph. Now, a little thing about map making is that every planar graph can be colored with at most four colors. That's a fun fact. So no matter what it is, like even if it looks like this, I'm gonna stick a guy over here and then guy. And then we can color this in 4 colors. So let's try and do that. So I color this side black. And because these two this edge right here, or not edge, this face right here is touching this face. And so is this one and this one. We have 3 different colors. So we can keep the outside face. Let's do gray. That just looks like black, honestly. We make this one light gray. Alright, and then we can make this one right here black. And therefore, we only have 4 colors. So yeah, that's true. Any planar graph could be colored with 4 colors. And map makers found this out a long time ago, but it took a really long time for that to be proven true. Remember, I was late to class. Why is it important to know if our shapes are coplane? It's not. So we're talking about graphs, and the graphs are planar if you could draw a graph without the edges crossing. And the reason why we want to know if our graphs are planar is because we could do cool things with them. We could color them. Is it important in life? I don't know. Is it fun? At least to me it is. There's a couple things we can do for planar graphs. Yeah. More stuff about planar graphs. Okay, so let's talk about Euler paths. Remember Euler? That was a guy. So an Euler path is a path that visits every vertex exactly. Wait, no. An Euler path is visits every edge once. So like, yeah, a path like this. Let's get a different color here. Ew, orange. You like orange? I like. That is not orange. That is sad orange. I don't like sad. We go here. We go here. We go here. We here. We visit everything once. Meanwhile, a Hamilton path visits every vertex exactly once. So let's draw a graph. I don't know. Like this. Then we could take red. And then just, yeah. Well, it just looks like I just drew the graph, but give me a second. Okay. Let me show you another problem that I think you guys might have seen. Alright, so the problem here is this little house problem, and people usually ask, can you draw this house without lifting your pen? And this is an Euler path problem, where you have to visit every edge exactly once. And the thing about this problem is because you have to start at this one or this one. We could go up here, up here, up here, up here. Or in another way to draw this. Where do I go? This weird notation, I use, yeah, it's kind of hard to understand. It's kind of hard to read it when it looks like that. But yeah, or we could start over here. We could go like... Oh, never mind. I go there. Yeah, we could go like that. But the thing is, if we start here, there's no way for us to reach every edge. See, there we missed that one. Start at the top. Miss that one. That. Well, we get stuck there. If we start from here, we could try that one. So yeah. We have to start at these bottom two. And the reason why is if you count how many edges everything has, this one has 3 edges. And you can count 1, 2, 3 to find that there's 3 edges. This one has 4. This one has 4. This one has 2. You'll find that these guys have an odd number of edges. And the reason why we have to start there is because Euler paths have to have 2 odd vertices because so you enter here and then you leave. So then eventually you have to get this edge back, you have to enter it eventually again. Meanwhile, for these even ones, let me do 2. You enter this. So let's say we go into here, but then you leave. And you can never come back to it after that. Which means we can't start at any of these. Because a start kind of counts as entering. So yeah, in an Euler path you have to have 2 odd vertices. Professor Layton, is discrete math? It's always been... It's been graphs? It's always been graphs? It's been graphs this whole time? Mama, are you a graph? Yes, son, I am a graph. It's been graphs. Yeah. There's a little house problem. What the heck? Wait. No. There. I forgot how to use Krita. Where am I? What am I pressing? Okay. That's a cool little graph, right? Yeah. So yeah. Oh yeah, by the way, planar graphs have to be connected graphs, by the way. So a connected graph has to have an even number of vertices, which is why you can't just have one odd degree vertices. Vertex. I don't know how to say words. But yeah, connected graphs always have even number of vertices. If like odd one. Yeah. That guy has to be connected to like that guy and that guy. Like you have a one right here. That guy has to be connected to that guy and that guy. Yeah. Something about connected graphs or whatever. Anyway. Yeah, so 2 odd vertices, it has an Euler path. An Euler circuit is a little different. So an Euler circuit says we start and end in the same place. Meanwhile, an Euler path, or this is just about paths in general, and circuits. So an Euler, or a circuit says we have to start and end at the same place. A path says we just have to start at one place and get to the other place. So here's a little way to check if something has an Euler path or an Euler circuit. If a graph has 2 odd vertices, it has an Euler path. If it has no odd vertices, it has a Euler circuit. Euler, my bad. Euler circuit. If it has more than 2 odd vertices, it has neither of these things. And this is used to find paper routes to send your newspapers or to deliver milk to people. If you turn your entire neighborhood into a graph, you can like try and find the different ways where you could like get to places. Yeah, visit every edge once. Now Hamilton paths are a little different because in a Hamilton path you visit every single vertex once. So Euler path focuses on edges. A Hamilton path visits every vertex once. So this would be a Hamilton path. Or no, this is a Hamilton circuit. But if you do like something like this, and you went like this is a Hamilton path. And the thing about Hamilton paths is that they're kind of hard to solve. We don't have any efficient algorithms that can solve them in a... At least for the bigger ones. With the smaller ones, we can solve them pretty fast with computers. But with really big ones, or not big ones, like above average ones, it's hard to find Hamilton paths or graphs in a computer using, you know, our human methods are better as of right now. And this is called an NP complete problem, and that just means, yeah, they're hard to solve. How the heck Euler involved in every branch of modern mathematics? He's bored. Yeah. I think that's like the thing about Euler. Euler has a lot of things actually. Euler was bored. He was really bored at that time. I mean, to be fair, who wouldn't be bored at that time? No. All you have is pencils and papers back then. Nowadays, we have screens and tablets and... Okay, I wasn't trying to say... I wasn't trying to make a technology bad joke. I was trying to reference how I'm using a drawing tablet and a tablet pen to draw these graphs. Okay, back then we had paper and pencil. Nowadays, we have screen paper and screen pencils. And also, infinite videos to watch. But yeah. I mean, there's still a bunch of people making new maps nowadays, which I think is really, really cool. I feel like a lot of people don't realize that math is still evolving. It's just as much as a science as any other kind of thing. You know, there's still a bunch of stuff we don't know, and there's still a bunch of people looking to find new stuff. So there's a bunch of Eulers around here. Maybe not as Eulery as Euler, because like, you know, he was thinking a lot. Euler, like, oi, oi man. Oi, oi, oi. Okay, so... Oh yeah, wait, one last thing about graph colorability that I wanted to... Another fun fact that I wanted to show you guys. Cycles with even colors are 2 colors. Cycles with odd... What the heck are you talking about? Wait, hold on. Okay. So, I'm a little stupid when I write my notes. Anyway. I'll go fix those later. Anyway. Ugh. I don't like that yellow. Ugh. Nice orange. Nice orange looking guy. Okay. Yeah. Yeah, for this one we could just do follow. So every cycle can be colored with 2 colors, and that works for the vertices as well. You do like red, red. Do like blue, blue, and you could, yeah, it would look like this. Meanwhile, the even ones, you have to have 3 colors. Color them with 3 colors. You can't color them with 2 colors though. I wonder if the colors are like weird. I'm just picking random. I like color things. I love coloring, guys. Colors, am I right? Okay. Oh, and the chromatic number of a graph is the amount of colors you need to color the graph. Yeah. So yeah, remember when you color a graph, you can't have vertices that share the edge have the same color. You can't have edges that share a vertex be the same color, and can't have 2 faces that share an edge have the same color. So yeah, this is how many colors you need to color a graph. It's also kind of looks like this. This little guy is called Kai, by the way. This is a Greek letter. The Greeks have a lot of letters. I feel like we should like stop using Greek letters at some point and use like smiley. Just imagine that. Like we use smiley faces for a variable. That would be great. Euler was a different kind of beast, just like Laplace. I hope I said that right. I feel like you get one of those. What's a century? Yeah, and there's plenty of centuries that go by. I mean, with the amount of humans on Earth, there's gotta be at least 1 genius, statistically. But it's still great. We need one. I feel like if there were multiple per century, the world would be taken over. I think if like, imagine like there's like 10 Eulers in 1 century. I think we'd be gone. Are you the next one stream? I don't think I'm Eulery. I don't think I'm oiled up enough. I don't think. I don't know. I mean, if someone were to change all the variables of math into smiley faces, it'd probably be me. But other than that, I don't know what else I have to contribute. I just take the stuff that people have said, and I say it in a sillier tone. And that's yep. Oh. But to be honest, maybe anyone can be anything. You never know what's gonna happen. Okay. Alright, my last fun fact for you guys, which is pretty interesting, is about D&D dice. Oh yeah. Okay, so this is a dual of a planar graph is a weird thing. So we have complements of graphs, which, you know, basically reverses the edge relation. So like you got a graph that looks like this. Graph, yeah. And then you have another graph that like looks like and if you put them on top of each other, get a graph. Wait, I have technology! What am I doing? Wait. I'm gonna knock your socks off, guys. But yeah, if you place them on top of each other, you get like a whole complete graph. Yeah, that's cool. That's what a complement of a graph looks like. Duals are something different though. Duals, you take a plane. And then first thing you do is you label your faces. So we got face A, we got face in the dual of a graph, which we're gonna use red because I feel like that's kind of cool looking. We're gonna turn each face into a dot, a vertex. And then we're gonna connect these. So we turn every edge. Okay, how do I? Okay. So we turn the faces into vertices, and we draw edges crossing the edges of the original. It's kind of like I gotta like write it. Like you got an edge here. Okay, then that turns into an edge here. We have an edge here on the outside. Then we have another edge there. We have another edge here. We have an edge. Oh. This is our dual of a graph. Doesn't that look crazy? My socks! They were knocked off! Yeah, this socks... The socks are knocked... Whoa, that looks weird. But yeah, and then you could label like the different edges and faces up, like, yeah, you swap. Anyway. What can I do with this? Well, I don't know. Let's take a look at a couple graphs. We got a point here, we got a point here. Different faces. What the heck? I don't wanna write it this way. Yeah. Another one. I don't know where I'm going with this, honestly. Give me a second. Give me a second. My brain. But yeah, one little fact is the dual of a dual is just the original graph. So yeah, that's okay. Wait, I forgot to add. Okay, we'll just add it here. Okay. Actually, no, I want to put it on the bottom. What if we don't do that? Draw an edge here. That would. That one here. That one here. Yeah. Yeah, we have one here. Hello. Whoa, another one! I wonder if we could, straighten out these edges if they turn into something, honestly. But I'm trying to prove something that was told to me, but I'm not having a good, okay, hold on. Let's do black, actually. I feel like... if we straighten out the edges of this dual here... as you can see, okay, hold on. Let me move this guy over here, and I could show. But it's kind of okay. So if you put this in a 3D space, right, you get something that kind of looks like that. This is an octahedron. This is an octahedron. This is known as a D8. What I'm trying to say is, if you straighten out the lines and you go into 3D, you can make a D8. And that comes from what graph? This comes from this graph, which if you put into 3D, get like a D6, which is just a die. So actually, D&D dice are duals of each other. At least most of them are. Okay. That took me a minute to prove. But that's the sock knocking part, okay? Except for D10. D10's weird. We don't talk about D10. Because D10 is not a regular polyhedra. Which, what are we talking about? What the heck? Okay. So, we have our D4, which our D4 is... Wait, no. Kinda looks like... Right, and we take a dual of this one. As you can see, we get something like this. Which, if you rewrite it in a different way, it's the same thing! It's also a tetrahedron. Isn't that awesome? Okay, so yeah. So the D4 is a dual of itself. And a polyhedra, basically a regular polyhedra. Polyhedra is like... a regular one means that all of the faces are the same size. They're the exact same. This is made up of a bunch of triangles. Let's look at D6, which is our next polyhedra, which if we write as a planar graph looks, but in reality, this. Or well, I kind of that kind of looks bad, but you know what I'm talking about. And we have a D8, which planar graph form. I don't know how to draw this one in planar graph form, okay? But you gotta trust me. You gotta trust me that it looks like it's got it looked like this a little bit, right? Draw it like that. I don't know what I'm drawing anymore. Anyway, it kind of looked like this. It kind of looked like this. So if you take the dual of this guy, Yeah. It kind of looks like this, which if you rearrange in the 3D world, looks like this. And because we know that dual of a dual is the same as the original graph, the D6 and the D8 are dual planar graphs of each other. That's cool. That's a fun fact. I know you guys like fun. Oh, you're here. And the same thing can happen with the D12. I'm not gonna draw because it kinda look like it has the dodecahedron. Can I use this knowledge to get better rolls? Maybe. Maybe. You could tell the graphs, you could tell the dice, you know the secrets. I can feel my brain wrinkling to try and grasp for yeah. Yeah. Patterns and stuff. There's a pattern. They're duals of each other. Let me search up what a D12 looks like so I could try to draw it. I didn't even try my notes. That is not what I asked for. D20, D12, my brain's fried. Okay. Oh, it's a dodecahedron, guys! That means it got like little pentagons on there. Got little pentagons on there. And it looks like a soccer ball. You guys know what a soccer ball looks like? Yeah, like... And then a D20 kind of looks like this. Icosahedron. It's called an icosahedron. But yeah, you'll find that when you take the dual, if you turn these into planar graphs, you take the duals of them, they are each other, and that's cool. I thought that was kind of cool. So yeah, these guys are called the platonic solids, by the way, or at least most of these. We don't talk about D10. D10's kind of like the oddball of the group. I'm sorry, D10. You're a little weird. You're not like everyone else. That's okay. Still love you regardless. Have a head pat. I don't know if that looks like a hand. Let me... There we go. There. I love you. Yeah, those were some fun facts. I think. Well, there was this one more one. Saber, since you like cool science facts and don't know of Laplace, I will introduce you to a mind-blowing concept after you end the lesson. Oh, yes. Why don't you... No. I didn't mean to press that one. Yes. My brain was trying to return to my happy face, and then that's also the hotkey for my starting stream button. Yeah. What else? What? Oh, I didn't even talk about Eulerizing stuff. Eulerizing. Okay. One last thing before we end this lesson. Okay. One last thing. I think after I explain this, we'll have a little just chatting section. We could. Yeah. Okay. How to Eulerize something. So people use this to find mail routes and milk delivery routes and stuff like that, and you could save a lot of money by doing this. So remember how an Euler path tries to like take a visit to a path exactly once? Or like every edge exactly once? Well, probably drawing graph incoming. Oh! 1, 2, 5, 8, 9, 10, 11, 12, 15, 16. So suppose this is your neighborhood, right? Oh my god. suppose this is your neighborhood right here. Like little nice. Yeah, everyone loves each other. I'm not writing this correct. I'm doing wrong. Oh, I have too many guys, do I? I have too many. Okay. There we go. Okay, so suppose you want to try and find a route that gets through every single neighborhood, but you want to visit everything exactly once. So the thing about this graph, remember how we used the test for the Euler path? We try to see how many. We need 2 odd degree vertices. So let's write down the degrees of it. This is connected to 2 things. This 2, this is 4, this is 4, 2, 3. My bad. 3, 3, 2, 3, 3, 3, 4, 4. Okay. I'm just fixing it. I want to make it look pretty. Okay, so how do we find a path to here where we can minimize the amount of stuff we're going? We can... Well, to do that, we sometimes have to use edges multiple times. So basically what we do here is we reuse edges until we have only 2 odd vertices. So we can't drive through here. That would be like crashing through someone's house. We can go through here again. We can do this twice. Like we could go here, we could go here, we could go back down. So that's like adding another edge. Okay, yippee, yippee. So we want to turn these odd vertices into even vertices. Vertices. Is this used to find Euler paths or Euler circuits? Hold on. What am I doing? Please help. I don't know where I am. This is why I have my notes, guys. Oh, okay, so we're trying to find a circuit. My bad. Okay, we're trying to find a circuit, so we don't want any odd degrees. We don't want any odd numbers. So, okay, we're trying to find a circuit, which means we want to start at one thing, and then we want to go visit every single edge until we get back at here, but we want to do that in the least amount of edges. So, Mr. Paperboy, with his paper hat, he brings out a notebook, brings out this little paper, and then I gotta reuse some edges. So we're gonna try and turn these 3s here into 4s, or into 6s if we. So one way we can do that is, let's say we add another edge here. We're gonna use little curved lines to represent. So we added the edge here. This 3 gets turned into a 4, and this 2 gets turned. That's kind of. So we need to turn this 3 back into a 4. So we can put a little edge right here. This turns from a 3. 4. And this 3 turns into a 4. Okay, so we have a bunch of even. What about this guy? We want this one to turn into. To add an edge here, and then this one turns into. Now we got 1, 2, 3. That's cool. Now, all we have to worry about is, so if we add an edge here, this guy turns into 3. 4. This one turns from a 3 into a 4. Now the only other odd vertices left are these guys right here, and so we could just add an edge to them. We got 4 and 4. And then so erase the numbers here. Notice that everything has an even number of vertices, which means an Euler circuit possible. Let's try and find that. Do pink. I like pink. Or actually, let's do like a purple. What the heck? Hello? I want purple pink. Okay. So if we start from here, oh, maybe not that path. Go here. About this. And therefore, we have just our little paperboy here has found a route through the neighborhood that uses the least amount of edges possible, which means we save money! We save money and time, and little paperboy is very, very fast. Yeah, very, very, very fast, very efficient, okay? And that's how you Eulerize a path. So you can apply this to a lot of stuff. If you gotta go somewhere, you gotta go through a bunch of places at once. And you could like draw a little graph and be like, ah, I gotta go here and here and here. And then I just, the only times I need to return back over is to go somewhere. And yeah, and we save big money, guys. I think, according to my teacher, my professor, this Eulerizing whole thing, this kind of stuff, saved some mail company somewhere billions of dollars. You can save billions of dollars too now, guys. We are the masters of the world. We're gonna become trillionaires with this. Yeah. That took me 2 seconds to figure out. Or not 2 seconds, but like I had to take a minute to like think through it to make sure I Yeah, okay. That's thanks Euler. Thanks Euler. Thanks. It's not just Euler. Everything in math and science isn't always just one person. There's a bunch of stuff that, you know, some guy was thinking is, yeah. There's a lot of stuff that may come from one guy, but a lot of stuff is a collaboration of people. For example, this Eulerizing thing, how they save billions of dollars, that was multiple people working together. That's how the world is. It's not just one of a century guy. Most stuff is a bunch of one in a decade people getting together and putting their brains together to create a one of a century idea. And this is life. And this is Alright, I am toasted. So let me drink water. Optimizing my work commute with this? Yeah, you can! You can. Turn your life into a graph, and then you can use that graph to find everything. Except Newton, that little goblin worked alone. Okay, yeah, Newton did a lot of... There's some goblins that did work alone, yes. Okay, time to hit you with a mind warping. Yes, it is. It is time. Tell me about Laplace. I gotta search up how to pronounce his names correctly, because I don't want to be pronouncing this guy's name incorrectly for like the entire time. Laplace. Pierre-Simon Laplace. French polymathematician from 1749 to 1827. How do I pronounce his name? You're Simone Marquis de la Place. De la Place? Oh man, he died. I mean, of course he died. He's 17. It's from 1749. Okay, intro to the Laplace. Okay, it's Laplace. Okay. Okay, I had to search it up real quick. Okay. Laplace? More like, yes. Okay. So there are different differential equations. They're kind of difficult to solve, right? Okay, differential equations. Most of this stuff is in the real world progression model. Okay, okay. Okay. I'm bad at reading. Give me a second. Okay. Let me. Okay. My brain just like short-circuited, and you. Okay. 1, 2, 3. Okay. So there are differential equations that are kind of difficult to solve, right? Most of this stuff is in the real-world progression models that change with time, being time the problematic variable. Yeah, time is problematic. So this guy, Simon Pierre de Laplace, said, what if I transform the expression in a different dimension where time is constant? So you take your model to the timeless dimension, solve it there, and then transform the result back to your original dimension. And so are born Laplace transforms. Ooh, you're right. Is this why all the physics problems say assume friction doesn't exist? This one assume time is constant, and then you account for time not being constant. Ah, this reminds me of this concept in discrete mathematics called pi. Oh, it's basically in counting problems, you overcount the amount of stuff you have, and then you make up for the overcounting later, because it's easier to solve with overcounting. So for example, if you're trying to find how many combinations of stuff there are, which we did talk about earlier, let's say there were 10 Billy Boys, and you gotta sort them in 45 slots. Okay, you know what? This is not a good example. Let's say you're gambling. And then gambling, okay, let me see how many. You have to choose this amount of cards, you have to choose these types of cards to get the correct amount of. You gotta choose certain cards to get a royal flush. So you count the amount of royal. So you suppose order matters, and you say, well, I first pick my card, which is 1 out of. This is not okay. Gambling in a game where you have to make a set. You got cards, okay? Alright, so suppose order matters. Your first card would be like, I pick a card from the deck. And your second card would be like, I pick a card from the deck that complies with these rules. And then after that, I pick the last card, which complies with the rules. You're assuming order matters, which in a lot of card games it doesn't. But doing so, you can calculate the probability of each card, or how many total combinations of cards that you could pick where this whole thing is valid. And then afterwards, once you have found all the different combinations of cards that are valid in this case, you then divide it by the order of the cards, the possible orders of the cards, so that you don't overcount it. Because order doesn't matter in a lot of card games. You don't like pick a 7 first and then pick like an. You don't like pick a king and be like, man, if I pick a queen after this, it's invalid because I have to go queen then king. No, you just pick king and queen, and you're like, wow, I have king and queen. Those are good cards. Maybe we should do a stream all about calculating gambling odds. That would be kind of fun. You guys love gambling. I feel like gambling has gotten a lot of love recently. Yeah, I might look into Laplace transforms. It's weird that like, so how many ideas just come from people being like, what if I just make this simpler and then accounted for the complexities later? I feel like you can do that thing with life too. Like, if you have a lot of tasks to do, just like start simple and then account for the complexities later. Like, I have to write a bunch of papers defending the US Constitution. Let me start with a simple outline of the papers. And let me calculate, okay, let me account for this stuff. And then later I can add in the complexities. Yes. Yes. What if I make my life simple and account for the complexities when I die? Exactly! Live your life simply and then only get complex when you die. Because then you don't have to account for it because you're dead. I think I reached science nirvana. I think this is life. This is philosophy. This is everything. This is the world. This is where we are. This is the universe. This is time. This is life. And death. And complexity. And simple and discrete math. Yeah, let's go to a casino and count cards. Yeah, I want to learn how to like... Okay, that sounds really bad, Adam. I want to learn how to gamble. I think it would be very impressive to go up to like... I want to ruin board games for people. I don't want anyone to play Uno with me ever again because I'll be counting cards and be like, according to my calculations, you must... Oh wait, no, that's not the right voice. According to my calculations, you have a green 7. Yuko, I don't want to play with you anymore. Oh. This dude figured out dice trajectory and won Monopoly. Yeah, it's like that one anime that's like Kagakure, where they just gamble all the time, and then they just kind of like, I bluffed your bluff and I calculated, yeah. There's a roulette strategy where you exponentially increment your bet every loss until you win. Oh. Interesting. Why they establish a bet range. Yeah, honestly, if you go to the casino, you could like... You could do a lot of stuff. Like, with a little bit of math. Yeah. I feel like there's certain games that you... Roulette is hard to win on math. That's like your luck. There's other games though, like poker? Blackjack maybe? You could calculate the odds of that. I don't know how to do that, but I'm sure it's possible. And do you know, another fun fact is that a lot of these casinos, they hire mathematicians to calculate the best, like, betting range that you're allowed to bet in order to make sure the house always wins. But like they hire mathematicians to come in and calculate the odds of winning stuff, and then they use those odds to be like, okay, how much money should we make them bet so that they win sometimes but not enough, you know, the house always wins. Everyone should open their own casino in their own house. And that way, the house always wins. Wait, if everyone opens their own casino, and then everyone is the house, and everyone always wins, does that mean we have infinite money? I should become president. That's just the stock market. Yeah, but no. The stock market is rigged by the house of the stock, right? There's gotta be a house, the stock house. That's a thing, right? Yeah, no. It's like, if you own the house, you own all the money, right? If you bet the money, you know. Yeah. I swear my idea is different. Blackjack, yeah, you could get in big trouble for that, lol. Really? I get in trouble for doing math at blackjack? That's bogus. If I have the skills to gamble and win, I deserve it. I deserve all of it. What if the house takes a cut? It's now illegal. Wait, so if me and the house take cut, I can't take house cut of me? But that's my money! It's my house, it's my money! Why is it illegal? Give me my money. There's gotta be some way to get infinite money for everyone. Oh, but inflation is a thing. Whatever. If you're the house, yes. But wait. Okay. I'm the house. I think my brain just melted. But the house always wins. Therefore, the house wins the cut. I decree house is house, and you are the mouse, and stream where we analyze the implications of flat. Wait, that's fiat. I'm gonna assume that you meant flat currency because fiat. You know what? No, let's analyze fiat currency. Okay, I would feel better, but okay, hold on. Fiat currency, yes. I don't actually know that much. No, fiat. Okay, I wasn't sure if I was being stupid. Okay, I was. Okay, cool. Yippee! The house is always stupid. No, the house is not stupid. The house is silly. Okay, fiat currency. There might not be a stream where I analyze fiat currency because I don't know how to do that. let me look at it. Let me search fiat currency. Oh, fiat currency. Fiat currency, or fiat money, is a type of government-issued currency generally created by a central bank authorized by government regulations to be legal tender, but not backed by a precious metal such as gold, silver, nor any other tangible asset or commodity. That has intrinsic value because it's oh, so that's like just all of our paper bills and all of our credit cards. I'm gonna make so much fiat money. So all of our modern money. Yes, all of our modern money. Yeah. All of our money is not real money. What's stopping us from just... Okay. If society as a whole just decided that all of our money is worthless, that it is, because it's made up. Money is a social construct? Money is a social construct, everyone! We solved it! We just gotta stop caring about money. And then therefore money has no value. That actually... Yes, but we can't beat the society. The society. Oh, society. 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 Me when society? I can't believe society, honestly. I don't know why society couldn't come up with something like prettier for money. Like, why does it have to be... Okay, money doesn't look that bad. But you know, why can it be like pretty buttons? Imagine I carry like a bunch of little buttons around. Imagine like money was plushies, little stuffed animals. It's like rocks. Yes, rock. Well, that's basically just gold. But yes, imagine we carried a bunch of like rocks and seashells around. That would probably scratch all of our bags and stuff. You know what? Now I see why it's paper. We couldn't be pretty paper though. Like, you know, pretty paper. Maybe like with like smiley faces on them. Or maybe sad faces, depends on how you feel about money. And it's like, no. Or pretty flowers. Or little cute things on them. Yeah. I would say bones. Oh yeah, bones would be kind of hard to mass produce though. So, I mean, like, rocks, there's plenty of rocks everywhere. I'd assume all the rocks have to be, like, certain kinds of rocks. Because I just realized the practicality issue is if you have rocks in your pocket, it's gonna, like, scratch a bunch of stuff. Yeah. Ethically, yeah. I mean, yeah, we do have a lot of bones in general, but yeah. Again, it's the same problem, because, like, bones and rocks are gonna scratch all your possessions inside your pockets, so... Yeah. A cent costs more to produce than a cent. Oh yeah, they got rid of pennies in the US. We don't have pennies anymore. I kind of missed them. I like pennies. I used to eat I used to eat pennies when I was a small child. That was the first thing I ate. Well, not the first thing I ate. The first thing that I wasn't supposed to eat that I ate. I ate a penny. Just to carry around your bony bank. My bone bank in my bone bag. Yeah. Like, imagine you put, like, your phone next to your rocks and then your phone gets all scratched up. That's why we have to have paper. But it has to be pretty paper. Why can't the paper be pictures of rocks? I would like to look at a picture of rock every time I made a microtransaction. I would explain things? What would it explain? Are you talking about me eating a penny when I was a small child? That explains nothing. First of all, a penny. That's it. Do I look like a penny eater? I am European. Our papers are pretty. Well, let me search up European money. I know Canada has really colorful money. Euros. Euro. Oh, those are nice! See, they're colorful! Oh, that's pretty. Why can't we have... Oh, I'm gonna seal your money. I'll give it back to you in, like, a different form, but, you know. Oh, that's pretty. Oh, there's a little flower on the coin. Oh, that's so cute. Oh. Oh. You see, this is what we need. This is what the world needs. We need prettier money. Pretty money. So, do I look like a penny? Do I look like a penny eater to you? I didn't know that had a certain look. You know, I was almost proud. But now, I'm ashamed and humiliated. So what if I eat pennies? Or so what if I ate a penny once? You're not telling me that you haven't ever eaten any form of fiat money? That's what I thought. That's what I thought. US money is just boring and green, and it doesn't even have any accessibility features for the blind or anything like that. You have to, like, yeah, I'm pretty sure other countries have accessibility features on their money, right? Do euros have blind? Yeah, they have raised lines and perforations and braille. Yeah, braille. But like, US money, first of all, they're all green. So, yeah. And second of all, they don't have any like tactile stuff. So if you're colorblind, or if you're just blind, this is, yeah. No wonder why so many people in the US make mistakes. It's like, I handed you a $100 bill instead of a $20. I wonder why that happens a lot. Never ate money, but I did eat a plastic bag as a kid one time. A whole plastic bag? Did you were test ideal woman? I hope so. You don't know, you just hope so. Well, the stomach acid is pretty acidic, so I'd assume, depending on how many years, it's probably, yeah. Don't you have like a whole, oh, not the whole thing? Coward. I mean, no, I'm glad that you ate a reasonable amount of plastic bag. I'm glad you ate a reasonable amount. You know what? Yeah. Eating the whole thing would be. It's been like 20 years. Yeah, no, that bag is just gone. That's been disintegrated. I choked on my milk. My bad. You know, I'm glad you didn't die from choking. Eating plastic bags is dangerous. Let me state. All jokes aside, do not eat plastic. Do not eat coins. Okay, cool. It's a choking hazard. I'm saying this as someone who. I don't know if I want to admit this, but in high school, I ate a lot of. In high school, I went through a phase of eating plastic straws, and I would be eating the plastic utensils they gave us at lunch as a high schooler. I didn't swallow any of it. But I would just, yeah. I would eat lollipop sticks though. How did this start? I don't know! It was a weird phase. Why? I don't know! I don't know why! I don't know! I don't know! Listen, I don't have bones. I'm made out of paint. You know. I decided to just, you know, eat non-human things so I could see if I could eat non-human things. You know, whatever. Whatever. It looked tasty. It looked. It's okay. We all did weird stuff back then. Yeah. Yeah. It's a judgment-free zone. With judgment-free fiat money, judgment-free digestive tracts. I eat rocks though. I still eat rocks. Canonically. Canonically, I'm a rock eater. Anyway, you guys ready for the new mukbang stream? It's got on the menu. We got metal spoons, rocks, and zip ties. Yep, that's the mukbang stream. We're gonna eat those together. It's gonna be nice and crunchy. That's it, crunchy. We only judge you for your math skills here. What's 6 times 3? A charcuterie board. Yeah, I call it a character board. I call it a. I was trying to make a pun here. I don't know. Crunchy board. A charcuterie board. Yep. We have here on the far left we have indium. Solid indium. Here over this side we have a glass of mercury. And another dip. We have some crackers. You know, plain white saltine crackers. We also have some Ritz crackers and cheese crackers. If you like cheese crackers. We have grapes. We have metal bolts. We have white marble rocks. And as a nice refresher, we have bromine. The element bromine. Which its vapor is so toxic. One whiff of it will kill you. Anyway, enjoy! I think your Valley Girl bit is my favorite. I think your Valley Girl bit is my favorite. I wasn't even sure if I was... You mean how I go like, crunchy? Funny. I didn't realize that. I wasn't purposely trying to be Valley Girl, but now that you said that, that's the way to describe it. That's the way to describe it. The mercury is the palate cleanser, yes. So like, this whole board is totally gonna give you a cleanse of all the toxins and anti-nutrients inside of your body. You know, one sip of it is just gonna... It's also really delicious. and it's keto. It's keto for all you keto girlies. Keto. With more powerful toxins, it'll totally cleanse you of everything. And by everything, I mean everything. Yeah, you're gonna have such a slim figure with this because you will have no figure. It will have melted. Yeah, get ready to say hi to that 0-inch waist because you will have no waist. You will be turned into chemical waste. New luscious hair that they'll put on a wig on your chemical waste body when they bury you. Please restrain. It is the middle of the night here and I will wake nearly everyone up with laughter. Okay, I'll be normal. I'll be like fancy and refined. So may bod be ready for the summer? Yes. It'll be ready for the summer because you're gonna get that beach tan already from eating everything because your body will be shriveled up and cremated. That's a hot tan. And it'll be ready to swim in the ocean because as soon as you get into the water, you'll be all clear because you've dissolved. You've dissolved it. Pretty hot. That's so fetch. That's so fetch. Yeah. Now I want to do a whole stream of me just talking like that. The heat's gonna stiffen all the plastics we could see. Yeah, so the plastics are gonna melt inside and you're gonna turn ooey gooey goodness. That's gonna turn a lot of heads. All eyes are gonna be at you on the beach. I should change the category of this. We're no longer doing science and technology. I really hope that no one like clicked on this thinking, oh, they're talking about discrete mathematics? I'm so excited. And then I just proceed to just be like, anyway, we're all gonna turn into piles of mush. We're all gonna turn into mashed potato. It's gonna be so hot. It's gonna be this summer. Yeah, California girls are unforgettable. Antioxidants, toxins on top, hard top plastics, yeah, we are forgettable. Oh, 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 liver failure and brain damage. Lungs corroded, skin non-stop. Chemicals I put inside my mouth. Ooh, oh, 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 oh. I mean, technically you're putting chemicals into your mouth all the time. Technically. Because it's like, carbon is a chemical. Everything's a chemical. I don't know why people get so, like, wrapped up around, oh guys, there's riboflavin inside of my juice. It's like, yeah, that's like, am I pronouncing that correct? Riboflavin? Whatever it is. That's vitamin B3. I have, let me look at this. I had a random drink with me right now. Nah, I'm just gonna see. Oh man, I'm eating calcium. Oh, I am eating dihydrogen monoxide. Oh, that's so toxic. It's like, it's water. And calcium, it helps you with your bones. It is all atoms, bro. Trust me, bro. This arrangement of particles doesn't matter. It's... yeah, it's a matter. Yeah. Yeah, exactly. It doesn't matter. Well, okay, sometimes it matters. Because, like, sometimes... it's not the chemicals that are the problem. It's the certain kinds of chemicals. Like, just because you're eating chemicals does not mean they're bad chemicals. But at the same time, like, you know... you just gotta be careful with moderation. But just because something has a long name doesn't mean it's bad. I don't need anything I can't pronounce. Well, maybe you can't pronounce a lot of words. Maybe you need to learn how to read. I'm sorry, that was a little mean. But it's like, oh guys, I can't, what's another one? Acetic acid. That's terrible. That thing is in vinegar. What other? Calcium. I can't think of any chemicals, guys. I'm not. But like, yeah, it's. I only eat organic stuff. Cool, good for you. You like organic stuff. But you know you're still eating chemicals, right? You know, like, the apple has chemicals, right? Shut up and eat your salt, John! Exactly. Oh, I only eat, these saltine crackers. They're organic. They don't have any chemicals in them. Yeah, what do you think sodium is? Sodium chloride. Sodium chloride, what is that? Iodized salt? Sodium chloride plus iodine? Yeah. Yeah, how about You don't want to eat iodine? How about iodine's fist into your face? Yeah. Shut up, John. Shut up, John. Sorry, John. There's a John out there. Not all Johns do this. Ooh, get him. Yeah, get him. Wait, I got this. I got this. This is the first time I'm moving in like 15 minutes. Ooh, get him! Oh, get him! Get him! Iodine's nuts! Oh, get him! Oh. Yeah, we got him good. I mean, like, I'm not even that mad at people who, like, if you want to eat organics because it makes you feel, like, good about yourself, go ahead. Like, people can eat whatever they want. What I'm tired of is people trying to, like, spread all this fear around certain chemicals and stuff when it's literally just like, it sounds like niacin. That sounds like it could kill you. That's a vitamin. Cyanide is organic. Cyanide is organic, and yet, like, just because something is a chemical or has that chemical connotation to it doesn't mean it's toxic for your body. In fact, like, some synthetic stuff, some artificial stuff is better for you than some natural stuff. But yeah, I'm sick of people trying to make other people feel guilty for what they're eating. Which is why I think everyone should eat plastic and metal. Which is why I think it's okay if you eat paper and plastic straws, like me. And eat them together. Yukone, you have convinced me to vote for you. I'm running for president. President of the States. Yep. Mr. President. This is my order. And this is my broccoli cheddar soup recipe. Everyone gets a free sample of it at my presidential rally. Good job, guys. Of the States? Oh no, the world. No, I'm sorry, I misspoke. The States? I was referring to the states of matter. I'm gonna be president of solids, liquids, gases, and plasmas. Yep, I'm the president of all of those. Which means I'm the president of everything. You know the mechanical hands are the rulers of everything. I'm the ruler of everything. In the end. Yeah, we are Eulerizing this band. I kind of Eulerizing. I'm sorry, I keep saying Eulerizing. It's Eulerizing. It's just Euler. You know, I'm gonna use just math terms incorrectly, just all of the time. Yeah, guys, let's Eulerize this. How about you find a Hamiltonian path out of here? You're looking a little NP complete, girl. Man. Yep. Okay. Alright. Look, we're nearing the 3-hour mark, and as much as I would like to continue yapping, This is so peak. Yes, I think. I got water to drink. Okay. Anyway. I would like to thank you guys for coming here to watch me yap about discrete maths. I hope you learned a thing or two about graphs. And I hope you learn a few things about the set notation. Yeah. Thank you for coming. Thank you for telling me I should become president. And eat water, drink. Wait, hold on. Thank you for the stream. I always have a blast here. Please take care. Goodbye. Thank you. I'm glad that you guys are having a blast here because I'm having a blast here too. Yeah. Anyway. Okay, I'm dragging this out. Drink food, eat water, get your daily dose of plastics and metals. Fiat money is a social construct. And discrete mathematics. Goodbye!